All right, so we're going to go through these homework problems pretty carefully here, but let's review a couple of things. So this was what I had up in your notes for. This was from chapter 2, so we had this up yesterday. This is what we had learned about doing limits as x approaches a number. So like x approaches 2, x approaches 3, that kind of thing. Well, what we do is we do substitution. So we plug that in. So that's always where we should start. All right, so we plug that in. And what could happen? Well, you might just get a number. So the limit exists, that's your answer. What happens many of the times is you get 0 divided by 0, which we don't know if that means the limit will exist or not. A lot of times it's a hole in the graph, and there is a limit. Okay? But it's also possible that the limit doesn't exist. Could be a vertical asymptote, those kind of things could happen too. So we had a bunch of algebra stuff that we did. Now we might still have some problems where we could do that. However, this new L'Hopital's rule is something that we could use as well. And so it will give us another tool of what to do. So the new thing we have to learn today is not going to be a new set of limits. Matter of fact, when we learn about L'Hopital's rule, what we're going to do is go back on today's homework, and we're going to look at all of these homework problems as if we were going to try to use L'Hopital's rule and see if it applies or not. So the new thing we have to learn is not a new set of limits. It's just another way we could do some of these problems. And we'll find that on some problems it's going to be easier to do L'Hopital's rule, and other problems it might be easier to just stick with the way we've been doing it. Okay, so it's just another strategy we can use in helping us do these limit problems. Okay, and then we said that if you get a number, if you plug in and get a number divided by 0, then that's a vertical asymptote situation. And we also said that in that case, the limit does not exist, and we need to discuss the limit on both sides. We need to talk about what's happening to the left of A and what's happening to the right of A. Why does that not exist? Now, as I was walking around, I noticed on some of your papers you had does not exist, and that was all you had for your answer, and I did look real carefully. The rule for us is going to be you have to put, if the limit does not exist, you have to say that, and you have to tell why. Show why. Well, one way of showing why is the limit from the left and the limit from the right. See what's going on. Okay, then the other thing we learned yesterday, or talked about yesterday, is what about limits as x approaches infinity, or negative infinity. Usually, they work the same way. And what are some things that can happen there? Well, we might get infinity over infinity, which again is not 1, just like 0 over 0 is not 1. It might be 1, it might be 0, it might be infinity, it might be a lot of different things. It's called indeterminate. So this section right here is what we call indeterminate. We don't know if the limit exists or not. We got to do some other stuff to it. Okay? And so, and one of the things we learned with infinity over infinity was high powers dominate. The high powers, if you have a higher power, as x gets really big, right? And another thing we talked about is it's the rate of infinity or 0, etc. In other words, it's how big. If you have infinity over infinity, what you really have is a number getting big on top and a number getting big on the bottom. What really matters is which is getting big faster. Or if you have 0 over 0, you have a number getting small over a number getting small. What matters is which one's getting small faster. That's what determines what the limit's going to be. So these are the things that we have to deal with in this situation. And again, down here, you could get, what would be another example that does not exist? Well, we talked about limit as x approaches infinity of x squared. Right? You just have that just going out to infinity. Well, that does not exist. And we would just say that's infinity. But we don't want to, that can't be our only answer. We have to say does not exist, and then we would say because it's going to infinity. Okay, so it doesn't have to be a vertical asymptote for the limit to not exist. It could be that kind of situation there. Well, matter of fact, why don't we write this down? How about we do that? Let's just write down examples of limits that do not exist. Now today in the homework there's going to be some graphs too. So on the quiz there might be some graphs. I think those are easier, quite honestly. If you have a graph, I think limits are easy to do. So give me some examples. Let's write down the different examples we can think of a limit that would not exist, both graphically or an equation. Okay, if you get a number over 0, so if I get 7 over 0. Okay? So if I'm doing the limit as x approaches 2, let's say, and I get that, then what we would have to do is check 2 on the left. We would have to check 2 on the right. Usually what happens in that situation is maybe you get infinity for one of those, you get negative infinity for another one of those, and that's what you'd have to have for your answer. So you're checking as x approaches 2, you plug a 2 in, you get 7 divided by 0. Right away you know that means does not exist. It's a vertical asymptote situation, so we want to check the left and the right, see what's happening. Now, the other thing is if this was just a graph, you might be getting this kind of deal, right? If it was a graph problem, we'd be talking about that situation, right? The limit does not exist, the cars don't meet. On the left, it's going to infinity. On the right, it's going to positive infinity. But we would, in either of these cases, if it was a graph or it was a plug-in problem, we would have to have this as our answer. And we would have to show that, or we would have to say that that's what's happening. Okay, I guess maybe we want that part of it too. Then. So we'd have to say that that's what's happening. Okay, what's another situation where the limit doesn't exist? What's that? The one that was x squared? The limit as x approaches infinity of x squared, right? Comes out to be, I mean, that just gets bigger and bigger. Now, again, we need to put does not exist on one like that. We would need to say does not exist. Like at the end of the video yesterday, it said, it really isn't accurate to say a limit equals infinity. Limits always equal numbers. That's what we were talking about here. When a limit exists, it equals a number. Infinity is not a number. So we can't say a limit equals infinity. What we can say is it does not exist because it's going to infinity. All right? And there'd be one more I could think of, and this would go back to chapter 2 in the original videos we saw. Yeah, that would be where the cars don't meet kind of a situation. You could have this kind of a situation where the limit does not exist. But again, the same thing is true. Let's say this was at 3 right here. So we'd still have to see as x approaches 3 from the left, and we'd have to say as x approaches 3 from the right. Now maybe this is a value of 1 here from the left, and maybe this is a value of 2 here from the right, you know, and we can have that situation. So instead of going to infinity and negative infinity, like in a vertical asymptote situation, we might have a piecewise function situation. The limit doesn't exist. So again, you're doing the limit. So no matter what, whenever you give, I mean, that's about all I can think of with does not exist. Limit does not exist. And no matter what, when you say limit does not exist, you've got to have more stuff with it, right? You've got to have something else with it saying why. So my directions on the quiz will be something like, you know, if the limit does not exist, check the one-sided limits. Oh, well, that doesn't really help you for that one. Maybe it'll just say show why. Show why it doesn't exist. Okay? And that's what you've got. Okay, so that's something that's important to be able to do. All right, let's go through the homework real quick. So, number 9, as x approaches infinity, big on the bottom, so the answer, 0, right? So basically what you have here is like 3 divided by infinity. Now that doesn't, you know, in your book, I think it's on like page 223 or, man, if you want to go to that, in your book on like page 225 or something, they've got this little chart, and it goes through some different uses and misuses of infinity. It's kind of a interesting little chart to read through. But it talks about 3 over infinity. Sometimes people say, well, 3 over infinity equals 0. Well, technically that's not right. Infinity's not a number, so you can't really talk about equals. But what you're saying is 3 divided by a really big number is getting to be a really small number. That's what that means. And that's what we're talking about here. Okay, so the answer is 0. Number 10. What do you got? Also 0, because again, on the bottom it's getting bigger and bigger and bigger. The top is 5, and it just, now in these you won't have to show any work or anything. You could just, you know, on the quiz you got those, you just put your answer, right? Just like that, same thing. If the limit comes out a number and you can just calculate it based on these strategies we've used, that's good enough. Okay, what about 11? Negative 1/2. Now, this is one of those where we talked about, hey, and we're going to talk about this with this new L'Hopital's rule here in a little bit, but As t gets really big, the 3 doesn't really matter. 5 doesn't really matter. So you end up with 2t over negative 4t. The t's cancel, and that reduces to negative 1. Okay, very good. All right, let's look at number 12. What do you got number 12? 3/5. Very good. They were trying to not trick you, but they were trying to make the point here that here you have the same exact function, but two different limits, and so you treat them differently. On this one, t is getting very large. So we're saying that the 3 doesn't matter because it's like 2 trillion and 3. Well, the 3 doesn't matter. 5 take away 4 trillion. The 5 doesn't really matter. So we can kind of ignore those. But in this one, they do matter. Here, t approaches 0, we plug in a 0. Plug in a 0, you get 3. Plug in a 0, you get 5. There you go. That's like we were talking about back here. If you get a number, if you plug in and get a number, that's your limit. You're done. Okay? So 3/5. All right, 13. Does not exist, and we want to have that with it. So that's what you would have to have on your problem. Now, how do you want to do that? You wouldn't have to show anything. You could just say, hey, the top's getting a lot bigger than the bottom, so therefore that fraction is going to just keep getting bigger. That's a good way to think about it. Or you could say, hey, x squared, the 1 doesn't matter, so this is x squared over x, which would reduce to x. So as x gets really big, what's that do? It gets really big, and so it goes to infinity. So that'd be a way to think about it too. But you wouldn't have to go through that to reason your way through it. So when we get this new L'Hopital's rule thing, it will work on this problem. But I'm not sure you would need it. It's pretty easy to just look at that one and tell what it is. Okay, so this new thing is just going to be an additional tool you have if it's needed. All right, how about this one? What'd you get? 1/2. Now, the way we explained this one is we said as x gets really big, the 1 won't matter, the 3 won't matter. This would be x squared over 2x squared. Those would cancel, reduce to 1/2. And that's a good way to do it. Okay? 1/2. So there's a case where we had infinity over infinity, but it does not equal a 1. Okay? It equals a 1/2. It's based on how fast those are getting big. 15. 0. Sign is going to go from -1 to 1 when x gets big. So way out at the far edges of the sign graph, it's just going back and forth, -1 to 1. This is going to keep getting bigger and bigger. So this fraction is going to get smaller and smaller. It's going to alternate from positive to negative, but it's going to get very small. So the limit is 0. 16. And we need more. Negative infinity is correct. Now, this was a little bit of a tricky one. The top's not too bad. The top's just negative infinity, right? Because you cube a big negative, it's going to be another big negative. But what's happening down here? Well, now, see, here's the thing.
Either way you do it, it doesn't matter.
Okay. It'd be -1 to 1. See here? Right. Right. But I think the 2 matters. That's the interesting thing here. When we were talking back here, the 1 doesn't matter, the 3 doesn't matter because x is getting really big. But here, when x gets really big, does this get really big? No, right? And so the only time the 2 wouldn't matter is if this part was getting really big, then the 2 wouldn't matter. But it doesn't. This part's just going from -1 to 1. Matter of fact, I want to talk about what would happen if the 2 wasn't there. We'll talk about that in a second. So this goes -1 to 1, and you're right. Then when you add 2 to that, that's going to go from 1 to 3, right? So which keeps it positive, which is really kind of important. So since this is just a number from 1 to 3, and this is going to be this huge negative number divided by a positive, it is going to be negative infinity. So that's correct. What if this was just x cubed over cosine? Yes, see then, but not only that. So this could be -1 to 1. This would be negative infinity. Well, yeah, because this could be 0 down here. And It could be negative infinity or it could be positive infinity. So what's happening is every time cosine is 0, there's a vertical asymptote. And then this thing's going negative infinity, then positive infinity, then negative infinity, positive infinity, back and forth. And so what happens is there really is no limit here. And so this is actually one we haven't really talked about. Here the limit would not exist because it's continually alternating between negative infinity and positive infinity. So that's another reason why it would not exist. Different than what we've seen before, and I don't anticipate you seeing one like this. So the 2 actually does change. Either way, it does not exist, but for different reasons. Yeah. Well, a little bit. Yeah, in the sense that that's kind of what the secant graph does. It goes up, and then it goes down, and then it goes up, and then it goes. So from that standpoint, it would be a little bit like that. Yeah. The only difference is since this is getting bigger on top, it's not a 1. It would be kind of changing, but it would be similar. You could graph that and kind of see. I'm not sure it'd give you a very good graph, actually. But, so it does kind of change things if that 2 isn't there. But the 2 being there makes the bottom always positive, which is nice, and then that makes it a little easier to see. All right. So that's one that you really kind of have to reason your way through. And that new rule we get today, the L'Hopital's rule, won't work on this. So it won't work. So some of these problems, the only way to get them is to kind of reason your way through what those functions do. All right, 17. Does not exist because it goes to infinity. The top gets way bigger than the bottom. We talked about that. Exponentials get bigger than powers faster, and so therefore the top's going to get bigger than the bottom, so it goes to infinity. Okay, what about this one? What about 18? 0. Because what happens when you put a negative number into 2 to the x? Yeah, it's like it flips. It does this, right? It gets smaller. It's like 1 over 2 to the whatever. And so that's going to get smaller. This is going to get bigger. So this is really going to get small because in a hurry. Because this is getting really small while the bottom's getting really big. Both of those make the fraction get smaller. So that one's going to go to 0. Okay, so same function. Different result based on infinity or negative infinity, which is kind of interesting because sometimes that doesn't happen. A lot of times, positive or negative infinity give you the same basic answer. Okay, what about 19? Now, I know this one's in the back. And what is it, 0? I think it is 0. It is 0. Now, I'm curious, though, what your reasoning would be here, because I think this is a tough one. Why did you have 0? Now that I've said that, of course, I've scared you into answering, right? Because now you think your answer must not be right. Do you know what the graph of natural log looks like? You should. We need to. Crosses at 1. That's the graph of natural log. So as x gets really big, what's natural log do? Getting bigger. And it never levels off. It gets close. I mean, it gets pretty flat, but it's never quite levels off. So it's getting bigger and bigger and bigger. So the top's getting bigger all the time. What about x to the 2/3? What happens to that when x gets bigger? It gets bigger. Yeah, it gets bigger too. I mean, not as fast as like x would, but it's it's a cube root. So as x gets bigger, you cube root it, it's still getting bigger, and then you square that, so it's getting bigger. So it's going to keep getting bigger also. Now the question is, which one's getting bigger faster? I don't know exactly. I think that's why this is a hard one. I don't really know. Actually, here's what x to the 2/3 looks like. What you have to do is first take x to the 1/3, which is the inverse of cube. So here's a cube here. Here's what cube root looks like. Oops. Here's x to the 1/3. But then if you square that, it makes all these values get a little bigger and a little more positive. So what happens is it just kind of goes up like this, and then this one kind of goes up like this. And so that's the graph of x to the 2/3 right there. Okay, it comes down like that, and then a v, there's kind of a sharp point there, and then it does that. But it gets bigger too, but kind of like log does. It's kind of flat. it's pretty flat. So the question is, which one gets bigger faster? Well, it turns out this one gets a little bigger, a little faster. Why is that? Well, it's because natural log is the reverse of e to the x. Remember we said an exponential gets big really fast? So that means this gets big really slow, the reverse of it. So this one down here gets big faster than this one does. And so that's why the answer to this is 0. However, this is, and we're going to come back to this later, this is one where L'Hopital's rule would come in really handy. Because you know they're both getting big, or maybe you don't even know they're both getting big. You should, because you need to know what the ln graph looks like. Okay? But which one's getting big faster? Sometimes we know, like this one we know. This is getting big faster than that, so we just knew that one. But this one we did. So we'll come back to that, and that's where L'Hopital's rule can really come in handy. Okay, what about 20? The answer is 0. Now, really what you have to do is it's like a limit problem, and then, so you really have to do this limit problem here. So you really have to say, okay, x is getting really big. What's this approaching? Well, that's going to 0. If x is getting really big on the bottom, this is going towards 0. So then what you have is sine of 0. And that's just 0. Sine of 0 is 0. So that's why the answer there is 0. Okay? And then, what about this one? There you just plug in, right? There's nothing weird going on there. Sine of 0, 0. Sine of 0, 0. And so you get that. All right. And then we had this last one. Now, the reason I put this one on here was because we never, in all those book problems, we didn't have to do one like this, right? Like this, right? When we never had any there where we got like a 7 over 0 or 11 over 0 or something like that. And I want to make sure you can handle those. We had some like that where it just gets bigger and bigger. We didn't have any of those, but we had some of these situations, but we didn't have that one. So I wanted to make sure we could do that. So when we get to this one, we plug in a 3 and we get 14 over 0. So right away, that tells us this is a does not exist. But we've got to check x approaching 3 from the left, and we've got to check x approaching 3 from the right. Anytime we get a number over 0, we know that's what we've got to do. So 3 from the left would be 2.999. 3 from the right would be something a little bigger than 3. And then we plug those back in. So 2.999 squared is about 9 plus 5. So that's basically 14 over what? Small negative, right? Because it'd be 2.999 minus 3. So that's a small negative. And I think just write that. And so that's going to be negative infinity right there. And if you do a little over 3, that's still going to be about 14. But if you do a little more than 3 minus 3, that's going to be a real small positive. And so positive divided by positive, small positive, that's going to be positive infinity. So those two pieces of information along with does not exist is what you want to have. Okay? So expect something like that on the quiz. All right, that's a vertical asymptote situation. Vertical asymptote at 3. On the left, it's going down. On the right, it's going up. That's what's happening. All right, let's move on then, and we're going to come back to those problems, but we're going to show this new thing. So on some of these problems we just did, there would have been another way we could have done it. It's called L'Hopital's rule. Now, it's written in your book on like page 229 or 227 or 220 something. I can't remember which page it is, but it doesn't really matter. I'm going to write it a little differently than they do in the book anyway. I did notice in the book it wasn't a capital L, though. Yeah, it was a lowercase L. It's got the little hat or carrot symbol on the O or something. So I don't know if that means L'Hopital. It's long O. What is it? L'Hopital. Is that what it means? L'Hopital. The hats mean nothing in French. Okay. Oh, okay. Well, that's good. I learned something new. They're just there. All right. So here's what this says. L'Hopital's rule says, if the limit as x approaches a of f of x over g of x, and that's the key, it's got to be a fraction kind of a problem. If that equals 0 over 0, or the limit as x approaches infinity, and it could be negative infinity also, of f of x over g of x equals infinity over infinity. Now, I suppose it could work the other way around. You could have x approaches a, or x approaches infinity could be a 0 over 0, too. Bottom line is, if in any limit problem, if you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule. But that's the important thing. You have to have that, or L'Hopital's rule doesn't apply. And not every problem has that. Not every problem comes out 0 over 0 or infinity over infinity. So sometimes we just have to reason our way through it. But if it comes out one of these, we can use L'Hopital's rule. We don't have to, because we've already done a bunch of those kind of problems without knowing L'Hopital's rule. So you can still do them that way. But you can also use this new rule to do them. So here's what it says. So if you have one of these situations, 0 over 0 or infinity over infinity, then we know that the limit as x approaches a or infinity, either one, so I'll put them in one, of f of x over g of x, we know that that is the same as doing the limit as x approaches a or infinity, either one, of f prime of x over g prime of x. Well, we've already been hinting at that all day yesterday. We said that what determines, if you have a small over a small or a big over a big, what's going to determine your answer is how fast they're getting small or getting big compared to each other. So what L'Hopital's rule says is, if we want to do this limit, we need to know how fast they're getting big or small, do the derivative, because that's what the derivative is. It's the rate of change. So we can do the derivative of the top and we can do the derivative of the bottom and compare those to each other. Now don't confuse this with quotient rule. L'Hopital's rule is not saying do the derivative of this fraction. If you do the derivative of the fraction, you have to do the quotient rule. So those of you still having to take the gateway test, right? If you're doing the derivative of a fraction, you have to do the quotient rule. What L'Hopital's rules say is we want to compare the top to the bottom here, how fast they're changing. So we do the derivative of the top, we do the derivative of the bottom, and then do the limit of that. And if you still get 0 over 0 or infinity over infinity, do it again. Do the derivative of the top, derivative of the bottom. Okay? But that's a whole different question than doing the derivative of a fraction where you have to do the quotient rule. So don't confuse those two. So let's go back and look at the homework. And let's see if we had any of those. Let's see how many of those we had where we could have done L'Hopital's rule. And you can put them just off to the side. You can do it in your notes or you can do it in your homework, whatever. I don't care. So, number 9. Is this a L'Hopital's rule? It's 3 over infinity. It's not a L'Hopital's rule. So we would have just done this the way we did it for today. Okay, number 10. Again, 5 over infinity. That is not a L'Hopital's rule. What about 11? Isn't that infinity over, it's actually infinity over negative infinity, which is fine. So yes, we can use L'Hopital's rule. So what's L'Hopital's rule says? It says take the derivative of the top, which would be 2. Take the derivative of the bottom, negative 4. It works. Pretty cool. Which you can see that's kind of the same thing we did when we reasoned our way through it about high powers dominate, insignificant, the 3's insignificant, the 5's in. You can do that one either way. Doesn't matter. All right, let's go to 12. What about that one? L'Hopital's rule. Plug in your 0, you get 3/5. Oh yeah, that's just one where you just get the answer right away. So there's no, the biggest problem people have, to be honest, well, there's 2 problems people have with L'Hopital's rule. First one is they use it all the time. You can't use it all the time. So people want to use it even when it says, like, well, there's a section in the homework that says, use L'Hopital's rule for the following limits. So it's a pretty good bet you're going to have to on all of them. But I think you ought to get in the habit of always checking first. Plug in see what you get. If you get 0 over 0 or infinity over infinity, then you can use L'Hopital's rule. All right, 13. Top's getting big, bottom's getting big, infinity over infinity. So what's the derivative of the top? 2x. Derivative of the bottom? 1. So, now, here's another place people go wrong with L'Hopital's rule. Is they just keep doing it, they keep doing the derivative again and again. No, if you get 0 over 0 and infinity over infinity again, you can do L'Hopital's rule again. But right now we don't get that. We get infinity over 1. Well, that's just infinity. So again, there's our answer. So remember, once we do the derivative of the top, derivative of the bottom, we then have to plug back in again and see what we get. So x goes to infinity. This derivative, or this limit, is infinity. So it does not exist. 14. That's infinity over infinity, right? So, derivative of the top, 2x. Derivative of the bottom, 4x. Now, at this point, you have a choice. Right, the simplest is just cancel the x's. Right? Cancel the x's, you get 1/2, and you're done. Or you could say, okay, now, it's still infinity over infinity, so do it again. Derivative that's 2, derivative that's 4, and you get 1/2. But be careful. Don't just keep doing those derivatives because you might not be able to. Like right back here, if we'd have done the derivative, this is 2, the derivative of that's 0, and then we'd have really had trouble. I guess you could have said, oh, 2 over 0, that does not exist, but that's pretty weak right there. You just can't get lucky there. All right, what about this one? Negative 1 to 1 over infinity. That doesn't fit L'Hopital's rule. Negative infinity over 1 to 3. That doesn't fit L'Hopital's rule. So we're just going to have to reason our way through that one. 17 was infinity over infinity. Okay, so this one would work. This is getting bigger, this is getting bigger. So let's do it. What's the derivative of 2 to the x? 2 to the x ln 2. Derivative of the bottom is 2x. So as x gets big, this is still getting big. And this is still getting big. So it's infinity over infinity. So we do it again. Now you might be able to tell, hey, this is getting bigger, a lot bigger than this, but if you didn't see that here, you're probably not going to see that there. So what's the derivative of the top now? ln2, ln2. Because what you have is just a number. ln2 is just a number hanging out there, so it just hangs out while you do that derivative. So you're going to have another ln2. And the derivative of the bottom? 2. Now you know you're done. Now the top's getting a lot bigger. The bottom is just 2. So that is going to infinity. So the limit does not exist. So there would have been a good one for L'Hopital's rule if you weren't sure about how those powers were going to deal, or were going to work out, or which one was faster. Okay, then we had this one with negative infinity. Well, this one would not be a L'Hopital's rule because we had 0 on the top and we had infinity on the bottom. So that one we just would do because we know it's going to 0, that one. So we would not use L'Hopital's rule on that one. Here's the one I said you really needed to do L'Hopital's rule because I think maybe it's a little unclear which one of these is getting big faster. But you do know this is getting bigger and this is getting bigger, so it is an infinity over infinity situation. So we're going to say, all right, what's the derivative of ln x would be 1 over x. And what's the derivative of that? Now what do? Now we want to know as x goes to infinity. Well, you could just plug in your infinity now. That would be 0 on top. So, well, see, here's the problem. I think we should simplify this with algebra first. I think the best thing would be to simplify this with algebra. So what I would do is I would flip this up here, this negative power. I think we should flip that, and this 2/3 would flip up there as a 3/2. So with 3/2, we'd have 1 over x, and we'd have this up here as x to the 1/3. Wouldn't that make more sense? And then what would that equal? That'd be 3/2 what would happen with that? And that'd be x to the negative 2/3, right? Because this would be x to the negative 1 times x to the 1/3, so you'd add those powers. So now that negative would flip to the bottom. So this would be this right here. I think that's what you should do with that, is simplify it. Because otherwise I think it's hard to know if you can keep going with your derivatives. Now what happens here is x gets really big. Bottom gets really big, right? And so and top stays 3, so this one is going to go to 0. So once you do L'Hopital's rule there, then it becomes obvious. But you did have some algebra you had to be able to do that with those exponents. Okay? So be ready to do something like that. All right, and then 20 was just pi over infinity, so that was 0, so that wasn't a L'Hopital's rule, and 21 wasn't a L'Hopital's rule. So again, I can't emphasize enough. L'Hopital's rule is just an additional tool you can use for 0 over 0 or infinity over infinity. It's a pretty good one on some problems. Some problems you don't need. Probably do it the way we've been talking about. Okay? All right. So let's talk about these indeterminate forms now. Let's talk about this 0 over 0, infinity over infinity, because there's one other kind of complicating factor, and we talked about it a little bit yesterday, but we talked about so many weird things yesterday that it got lost in the shuffle a little bit. So let's talk about these indeterminate forms. So the two that are the main ones are 0 over 0 and infinity over infinity. Whenever we get those, we've got to keep going. There's probably some answer, right? And these are the ones we can do L'Hopital's rule on. Okay, but the problem is there's one other one. There's this one. Okay? And we've got to be able to deal with it. So, again, let's say again, 0 over 0 means you got something small divided by something small. The problem is we don't know how fast they're getting small, and that's what determines the answer. And that's where L'Hopital's rule comes in. So how fast is this getting small compared to this? It's like which one wins. If this one's getting small faster, it wins on top. If the one on bottom's getting small faster, it wins. Makes the whole thing bigger. That kind of thing. Same thing with this. One's getting big, the other's getting big. Which one wins? Which one's getting big faster? Well, that's what you have here. Yesterday I said this. If you've got something small times something big, the big thing's trying to make the thing bigger when it multiplies. The small thing's trying to make it smaller. Which one wins? The one that's getting big or small faster, right? Fortunately, L'Hopital's rule doesn't work in this case. It only works in this case. Well, it turns out that anytime we have one of these, we can turn it into one of these. Okay, with the reciprocal. Okay, so yesterday I gave you these 3 quick examples. So let me show you. So, and of course, the first thing, I guess what I should have addressed is the first thing everybody thinks is this is 0, right? Well, that's because everybody always thinks these are 1, but they're not. And everybody thinks you take 0 times infinity, it's got to be 0. 0 times anything. No, 0 times any number is 0. But infinity is not a number. So the answer to this is not 0. Might be 0, but not automatically. So there's 3 cases. Okay, one case would look like this. Now on all these cases, we're saying x goes to infinity. So what if I had x? I'll just make real simple cases. So what if I had x times 1 over x? Well, that's infinity times 0, right? The x is getting big. 1 over x would be getting small. Which one wins? Well, neither one. They're the same, right? But look what I can do. I can rewrite that as x over x. Now it's infinity over infinity. Now in this case, it does come out to be 1, right? Because x divided by x is 1. So neither one wins. They kind of cancel each other out. Okay, the next scenario would be, say, x squared times 1 over x. Now again, that's an infinity times 0 situation. X squared is getting big. 1 over x is getting small. Which one wins? Well, I can write that as x squared over x. Well, that's an infinity over infinity. So we could do L'Hopital's rule. Now, we don't need L'Hopital's rule for that one. We can tell that that's going to reduce to x. and so that one's going to be infinity. So in that case, the infinity one wins, the one getting bigger. Well, we can see that, x squared. Now, we can't always see that, right? But in these easy examples, we can see it. The one getting big wins out over the one getting small. So the product gets big. All right, and then the third case would be x times 1 over x squared. Again, you got something getting big times something getting small. I can rewrite that as x over x squared, which again is infinity over infinity. But this time, the one on the bottom wins. It reduces to 1 over x, which goes towards 0. So in this case, the one getting big times the one getting small, the one getting small wins. And the product goes to 0. Right? So, whenever you get a situation like that, if you want to use L'Hopital's rule, if you can't tell which one's winning, the 0 or the infinity, then you can use L'Hopital's rule. But you've got to rewrite it so it looks like a fraction. So we're going to do 2 quick examples, and then I'm going to give you a bunch of work time today. So let's write down this one. Now, you might, unless the direction of the homework say use L'Hopital's rule, so I would want you to actually use L'Hopital's rule in that case. But on the quiz Thursday, I'm not going to say use L'Hopital's rule. I'm just going to give you a bunch of limit problems. And if it works and you want to use L'Hopital's rule, you can. Okay? So what do you get for an answer here? Anybody got one yet? It is 0. Right? It is 0. But what's happening? X is getting big, so this is going to infinity. If x gets big, since it's a negative power, it's actually going to get small. So this is an infinity times 0 situation. And we've talked about exponentials, how they change faster than powers. So the 0 is going to win. The 0 is going to win. But what's the way I could rewrite this? The easy way to rewrite this, it's easy because of that negative power. We can just flip that down to the bottom. And now we have infinity over infinity. Right? And because of what we talked about earlier, we know the bottom is going to get a lot bigger than the top. So that goes to 0. But let's use L'Hopital's rule. L'Hopital's rule says, hey, if you have infinity over infinity, you can do the derivative of the top, which would be 1, the derivative of the bottom, e to the x, and sure enough, now it's really easy to tell. Now, as x gets big, the bottom's getting big, the top is just 1. So 1 over a really big number is, of course, 0. So that's how we could have used L'Hopital's rule. Turned it into an infinity over infinity. All right? And last one. Now let's give you a little more time to think on this one. Might be helpful to draw ln a natural log graph here, by the way. Now let's talk about a little introductory stuff here. You see the 0 from the right. Well, you might not even pay attention to that in the beginning. You just plug in a 0, right? 0 squared is 0. What's ln 0? It doesn't exist, right? ln 0 doesn't exist. So this is why I said I think you need to graph. So then you realize, oh, okay, now I see why they did 0 from the right. What is ln of 0 from the right? Negative infinity. When you approach 0 from the right on ln, it's negative infinity. So what you have here is a 0 times negative infinity. Well, this is one we can't do L'Hopital's rule on, but if we rewrite it, we can do L'Hopital's rule. So now try that. Try rewriting that so we can do L'Hopital's rule. And what you need is a fraction. You need something on top, something on bottom. Okay, let's help get to the next step. What do you think about rewriting that? ln of x over what? I agree. Right? That's what you could do. Now you can't just move the x squared down to the bottom. That doesn't work. But you can do the reciprocal of x squared, which would be this, and move it down to the bottom. Okay? Now, it might be helpful to think of that as ln x over 1 over x squared. That might help you here. But now, as this approaches 0, we said this was negative infinity. Here, as x approaches 0, that's 1 over a really big number. Or excuse me, 1 over a really small number, which is getting to be big. So this is infinity over infinity. So L'Hopital's rule will now work. So let's do this in black. So what is the derivative of the top? 1 over x. The derivative of the bottom? Negative 2x to the negative 3. Now this reminds me of the one we did a couple steps back here, when we had to do all of this stuff with these x's, right? We had to do all this algebra. I think that's what we need to do now. I think we've got this. We need to flip this around. So we need to move maybe this up here. So that'd be 1 over x times x cubed. Leave the negative 2 down there. What's 1 over x times x cubed? X squared over negative 2. Now, do the limit as x approaches 0. What is the limit there as x approaches 0? Remember, what you do after you do L'Hopital's rule, you get it so it's infinity over infinity, simplify it a little bit, and then you got to go back and do the limit. So now as x approaches 0, what do we get? 0. Okay. 0, right? We just plug in 0. 0 over 2. 0 over negative 2 is 0. So this answer, once you get through all that, the answer is 0. Okay? Now, on the quiz, I had said on some of these problems back here that you would not have to show any work. I mean, like right here. Right here. 3/5. Yeah, you're not going to show any work on that. Negative 1/2. You may not have to show any work on that. You can probably do that in your head. So there's probably not much work you have to show. There might be some where I might specifically say, or I might expect to see a little work. In other words, let's face it, 0 comes up as an answer about half the time, right? You know what I mean? So I don't know what to do on this one. Maybe I'll put 0. Or maybe I'll put does not exist, right? So if it's a problem where I know that this would be a good example, where you're just not going to get 0 without, I mean, which is winning this battle? Which one, is this going to infinity faster than this is going to 0? I just don't think that's something you just know. Okay? And so probably going to want to see some sort of how you got that answer. Okay? But there will be many of them where you wouldn't have to have that. Okay, again, there's a little bit of a gray area there, but if I want to take away, take away at least something from, I think you just guessed on that. All right, so the homework, you got the rest of the time to do that. Whoops. Oh, that's our worksheet for tomorrow, I guess. The assignment sheet. So we're looking at this top line right here. Now, I'll make a comment about this here. There are some graphing ones, so you get a look at those. But right here out at the edge, I said 56 through 80, multiples of 4. But really, you should probably do more than that. I mean, what that is a whole bunch of problems, where about 25 problems or so where you just practice them. It's kind of like the derivative page where I said, well, let's do 10, and now tomorrow we'll do another 10, next day we'll do another 10. I think you ought to pick about 10 of those instead of do multiples of 4, because that's only like 5 or 6 problems. That's probably not enough to get much practice. I think you ought to maybe pick 10 or so of those. Pick odd ones. You can do limits on your calculator, by the way, right? You can go in the menu and the calculus menu, and limit is in there, so you can check your answer. Now, it's not going to give them quite the same. It won't say does not exist. I think it says undefined, or it might say infinity on some. Okay, so we'll write it exactly how we are, but you can check your answers on some of these with your calculator. But I think go through and do a bunch of those until you really feel comfortable with it. In this section, it says to do L'Hopital's rule on some of those, and so you kind of know you're going to, but you really still should check. Make sure it's a 0 over 0 or infinity over infinity. And don't do L'Hopital's rule again unless you know it's still a 0 over 0 or infinity over infinity. Okay? All right, so you got the last 40 minutes or so here to do your work. Tomorrow will be some work time too. We'll just answer some questions, help you out on a few things, review what the quiz is going to be about, and then work done. Study for chemistry or something.